we did a recap just a while ago, and now what we will do is we will look at the efficiency of the programs that we have done. And as I said, you could have the same problem being solved using multiple algorithms or multiple programs. So, which one is better than the other? That is what we want to find out. Let us take a simple example. Let us say I want to find whether a given non-zero positive integer is prime or composite. All of you know what a prime number is, what a composite number is. A prime number is a number that is divisible by none other than 1 in itself. Okay. So, other numbers are all called composite numbers. 1 is the only exception, it is called a trivial divisor. Okay. So, what would you do? Look at the definition. It says a number that is divisible by none other than 1 in itself. So, I can start with a simple program. See what we have here. Let us say n is the given number. We start with a variable I which is initialized to 2. We initialize a flag is prime to 1, and then if n is not equal to 2, then what are we doing? We are checking whether n is divisible by I or not. Then if it is divisible by I, then we reset is prime to 0, otherwise we increment I to the next value and keep doing this. And finally, if not is prime, then you say number is composite, otherwise you print that the given number is prime. This is a small segment of C code. Okay. Now, the question is, do we really need to run this prime classification program such that you check for every value of I? Can we do better than this? So, for example, any number. So, what do we mean a number is prime? A number is prime means if I take for example 13, the factors of 13 are only 13 in itself. On the other hand, if I take a number like 4, its factors are 2 and 2. If I take a number like 25, its factors are 5 and 5. Let us take 18, its factors are 6 and 3. And let us take 24, its factors are 2 and 12. What is interesting is, you have numbers here which are perfect squares, 4, 25, and then you have numbers which are not perfect squares. But what do we observe here? Clearly, if I take the square root of 18, the square root of 18 should be somewhere slightly greater than 4, because the square root of 16 is 4 into 4. So, it might be slightly greater than 4. What we see in the factors is there is one number which is less than the square root of 18 here. Similarly, here you find one factor which is smaller than the square root of 24. So, what it tells us is, I do not have to check for all the numbers going from 2 to n minus 1. All that I need to do is check up to the integer square root of the number, and if the number is divisible by any of the numbers up to the integer square root, then I do not have to test beyond that. Another thing that we also notice is, if a number is divisible by 2, what does it mean? It is a even number. So, for example, what we can do is we can eliminate 2, 4, 6, 8 from the division. So, what we can do is we can start from 3 and then increment, test with 3 whether the number is divisible, 5, 7 up to the integer square root of the given number n. And that is the piece of code that I have written over here. What are we doing again? We are again setting is prime a flag to 1. Then if number is greater than 2 and number percent 2 equal to 0, that means if it is an even number, then is prime is not true, and then you just come out of the program. Otherwise, what you do? You start with a divisor equal to 3 and keep checking whether the given number here, for example, if number divisor 3 number percent divisor equals 0, then you reset the is prime flag. Okay. So, what is it that we saw now? We look at the prime classification program that we looked at. We looked at two versions of it. There are even much better algorithms for prime classification, and you find that one program, clearly the number of steps that are required to execute the second program is much smaller than the number of steps that are required for executing the first program. So, what do we need now? We want to find out what is the running time of the program. So, how do you define running time? Running time clearly can be dependent upon the input to the program, quality of the code that is generated by the compiler, used to create the object code. It can also depend on the MIPS of the machine. What do we mean by the MIPS of the machine? The faster the machine, the quicker your program is going to run. But what we want to do is, what the compiler generates, we cannot be sure whether it's optimized very much. And MIPS of a machine, today I run my program on a Pentium, tomorrow I am running on a quad core or whatever. So clearly what we need is, we need to define this complexity in what is called a machine independent way. Generally, so what we do is, we define the size of the input rather than the input itself. For example, sorting a list of n elements depends upon the number of elements given in the list. What I mean is, if I have an array to be sorted, let us say I have an array with these numbers, let us say I have 2, 4, 10, 15, 25, 30, 60 and 12 to be sorted. Suppose I have something like this to be sorted, and I have another array with numbers, let us say which are very large. I have, let us say, 20,000, 10, 25,000 and so on. What we mean is, the size of the number does not matter, but as long as, what does it depend upon here? Both arrays are of size 8 over here, and that is what will matter when you are looking at the computation of the running time of a sorting algorithm. Generally, for number theoretic problems, we talk about complexity in size of the input, and the size of the input is actually defined by the number of digits it takes to write number. For example, if I want to determine whether this number is prime or not, the number of digits is 5. So, complexity is defined by the length of the digit sequence that make up the given number. Okay. So, let us formally define what is the running time of the algorithm. Running time of the algorithm is given by this equation. Let us say the algorithm takes as input some size n, then the complexity is, let us say, T of n equal to C n squared. That means it's quadratic in the number of elements or the size of the input that is given to the particular program. What is C here? C is a constant, and the units of T of n are generally left unspecified. Okay, we talk about T of n in machine independent way, and we are talking about operations that can be performed on an ideal computer. We will see in a while what we mean by operations on an ideal computer. And generally, when we are talking about T of n, the running time of a program, we refer to the worst case running time, that is maximum on all kinds of inputs. There are other types of time complexities which are beyond the scope of this particular course, called the average of n, which is the average over all inputs of size n, and the average n of course is computed assuming that all inputs are equally likely, but there are other algorithms which talk about inputs which are not necessarily equally likely, and the running time of such programs are also computed. But we will talk about very simple worst case time complexity. What you have to know is, there are two specific type of notations. One is called the big O notation and the big omega notations when we talk about time complexity of programs. What does it mean? T of n, when it is written as big O of 1 squared, it means that we can find two constants C and n naught such that when n is greater than or equal to n naught, then and for a particular value of C, T of n is guaranteed to run in less than C n squared time. Okay. Then what it is basically telling us is that if I have the input to the program in terms of a particular value of n, then if I write T of n is equal to order of f of n, then f of n is an upper bound on the growth rate. So, how do we define this? We define time complexity like this. Let us say this is T of n as a function of n. Okay. So, what is it saying? Let us say now the actual running time of a program was, let us say, 3n squared plus 2n plus 1. I would write that this is equal to Tn is guaranteed to be less than or equal to big O of n squared, which means this is going to be less than or equal to c times n squared for a value of c and n which is greater than or equal to some n naught. So, let us take this example. Let us take n equal to 1, then t of n equal to 6. Okay. Let us take now let us say that I take c equal to 1. Okay. Then what is it that we get? When I look at t of n in terms of n squared here, then t of n should be less than or equal to c into n squared and 1 into n squared. So, for what value of n will it get satisfied? So, now notice that I have taken c equal to 1. Okay. So, if n equal to 1, then what do we get? We get that t of n is greater than this. Take n equal to 2, n equal to 3, n equal to 4 and so on, and you can ultimately take a different value of c. For example, suppose I have taken c is equal to 6 for that matter, then I would have got t of n is less than or equal to 6 n squared for n greater than or equal to 1. Okay. So, basically what we are saying is now what happens for n equal to 2, 3 so on. So, what happens? I can, as n increase, what is happening is this is going to be for n equal to 1. For n equal to 2, what happens? We have t of n is equal to 3 2s are 6, 6 2s are 12 plus 4 plus 1. Okay. So, what happens when n equal to 2, I get 6 into 2 into 2, 12 into 2, 24, 16, 17. Therefore, it is still less than n squared. So, basically what we are saying is I have some t of n like this, and then the big O of n squared is going to be above this particular line. Okay. That is the meaning of this big O notation. And what does big omega say? It says that big omega is the lower bound. Okay. If I say big omega of n squared, for example, if c equal to 1, we can always say t of n is going to be greater than or equal to n squared. Okay. So, you have a lower upper bound for the running time of the algorithm and a lower bound for the running time of the algorithm. What it says is t of n, which is the actual running time of the algorithm, is going to be bounded on one side by big O of n squared and omega of n squared on the lower end. There are certain things that you must worry about. You must remember that when I look at big O of n, what is the meaning of it? It is a straight line. When I look at big O of n squared, it is like this. Okay. Suppose I say big O of 2 to the power of n, then what is going to happen? It is going to go even more steeply. This is called exponential running time, exponential in n, and when you have order of n squared, order of n cubed and so on, this is polynomial time. And this one, when it is big O of n, it is linear time. You also have one more big O of n. For example, for all values of n, if it takes order 1, what is the meaning of it? It is taking a constant amount of time, whatever be the value of n, that is another complexity. So, what have we seen? Basic idea of big O of n, because we are talking about worst case complexity, we will not deal with so much omega n, but we will look at big O of n. So, as a function of n, we see what the time complexity of the problem is. When n, for example, increases and the time taken does not change, then we call this constant time, big O of 1. When it is linear, there is a straight line. When there is, for example, n squared, n cubed are all polynomial, and when, for for example, it is 2 to the power of n, it is exponential. For example, what do we mean by 2 to the power of n? This is a very dangerous algorithm. When n equal to 1, the time complexity is 2, n equal to 2, the time complexity is 4, n equal to 3, the time complexity is 8, it grows extremely fast. Okay, so you should always worry about it. Whenever you write algorithms, what we try to do is we try to see if the more efficient the algorithm is. For example, linear time is more efficient than polynomial time. Polynomial time is more efficient than exponential time, and constant time is more efficient than any of these. So, this is what we will like to look at. There are other notations, the theta n, omega n, small o f n, small omega n and small o of n. These are beyond the scope of this particular course, but enough for you to know it. What are rules for computing the running time of a program? There are 2 specific rules, the sum rule and the product rule. Okay. The sum rule states that if a program is made up of 2 segments P1 and P2, what do we mean by this? Let me illustrate this. What this means is that I have a program P1 here, have another program P2 here, and I say then that this program P is made up of sum of 2 program segments P1 plus P2. Okay. Remember we saw in the when we did the recap that you can use assignment statements, make a big program, alternative statements a big program, combination of assignment, alternative, repetitive, whatever. So, what you do is you compute a time complexity of P1 separately, compute a time complexity of P2 separately, and use the sum rule to compute the time complexity of the program P. So, how do we do this? If the program segment P1 takes order f of n and the program segment P2 takes order g of n, we already know what the order is, g of n and f of n are functions of n, then the total time complexity of the program is the maximum of f of n and g of n. Okay. This is called the sum rule. So, what do we mean by this? If let us say this program takes t of n is sum big O of g of n, f of n, sorry, and this program segment takes big O of g of n, then the time complexity t of n of the entire program is order of max of f of n comma g of n. This is what it tells you. Okay. We will see an example in a little while. Before that, I would like to talk about another rule which is called a product rule. Product rule is P1 program is obvious, P is made up of P1 into P2. What is the meaning of this? What this means is that simply that you have some kind of a repetition block that is there. So, I have some kind of a loop statement here, and within this loop statement corresponds to, let us say, P1, and within this I have the body of the program P2, and basically it means that the program segment P2 is getting executed P1 times. Okay. Then what the product rule says is that if the time complexity, let us say for this one is T1 of n and for this 2 is 2 of n, then what the product rule states is the time complexity T of n is big O of I am sorry, T of n equal to f of n, and let us say this is g of n, then this is equal to order of f of n into g of n, the product of the 2 time complexities. So, let us see an example now. I have a small program segment again here, sum is initialized to 0, there is a for loop which sums the first n number starting from 0. So, now sum is equal to 0, it is an assignment statement, it takes constant amount of time, therefore, we say it is order 1. Look at this for loop, for I equal to 0, I less than n, I plus plus. So, this is again an assignment, this is a comparison, and this is an increment. So, all of these are basically like sum rule with 3 statements being executed, therefore, it takes the maximum of order 1. Then again here there is a sum and an assignment here, I have not written the rest of it here. So, it again costs you order 1, but What is the time complexity for the segment of each loop? This loop on the other hand is being executed n times. So, if you look at the outer program P1 here, that is going to be executed n times, therefore, it is order n. Okay. So, what are we doing now? So, this time complexity becomes, so for the segment of each loop is order 1, but time complexity for the entire for loop becomes order of n into 1, because n is the time complexity of this for loop, because it is executed n times, and the total time complexity of this algorithm is order of n. Okay. And before that we also had this what you call order 1 statement here. So, if you look at the time complexity of the entire program now, this is like program segment P1 and this is another program segment P2, and it is a sum program. Now, you have to apply the sum rule and you get that the time complexity for the program segment is order of n. Okay. Next, what we will do is we will look at another kind of complexity analysis. So, simple programs we know how to do, assignment statements we can evaluate, and loops we know that when you evaluate a loop you have to find out how many times a loop is executed. Before we go into recursive functions, I would like to leave you with this. How long does this program take to execute? Suppose I have I is equal to 1 and I say while I less than n, I is equal to 2 star I. Okay. So, what is the meaning of it? So, basically how many times will this execute? Okay. Normally students have this habit of saying when I less than n, they will say n times. That is not correct. For example, let us take n equal to 8. So, I started out with I, and let us see how many times this loop, this body of the loop gets executed, and let us take the value of I and n here. I equal to 1, n is 8, then I becomes 2, n is still 8 of course, then I becomes 4, n is 8, I becomes 8, and n becomes, n is still 8, and what happens? I is not less than n and you execute, you exit. Suppose n becomes, n is equal to 16, then what will happen? You will have 8 to 16 over here, and this will also be 16. So, once more it will execute. So, basically what we are saying is, depending upon the value of n here. So, notice that it is only from when you change from n equal to 8 to n equal to 16, it only executes the body of the while block one more time. Okay. When n equal to 32, I am sure you got it right, it will execute one more time compared to n equal to 16. So, if you look at it in terms of time complexity, it is approximately log n times, okay, not exactly, it is order of log of n to the base 2. Okay. Notice that, for example, first time when it executed 1, 2, 3, okay, and then next time was 4 and so on. So, the time complexity of this segment of code is log n. So, this is something that you must remember, that you have to look at the kind of computation being done with respect to the loop to decide how many times it gets executed. The program that I had given here, clearly we had done I equal to I plus 1 in the previous case over here. Therefore, it executes the n times, whereas this program which I have shown you does not execute n times. Okay. So, next thing that I want to look at is how do we analyze recursive programs. Okay. All of you have seen recursion in the C part of your course. So, what are we doing here? N is equal to n 1, then value set to, I am just finding the sum of elements in an array, I am just writing a simple recursive function. This statement is what is important. This is a comparator here, it costs order 1, order 1. Here on the other hand it is order 1, and the way you write it is, because it is a recursion here, it reduces the size of the problem which was originally n to n minus 1, and it is order 1 for the addition and the assignment plus t of n minus 1, because this function is going to be called again. So, what we do is, when you do time complexity analysis, and if you look at it, it is c plus t of n minus 1, some constant time if n is greater than 1. It is equal to 2 d if n equal to 1. So, in general I can write that t of n is I c plus t of n minus I if n is greater than I. Okay. And when I equal to n minus 1, what happens? C into n minus 1 plus t of 1, C into n minus 1 plus t, and therefore, the time complexity of this algorithm is order n. Okay. So, this is something, here is something that I want you to be a little careful about. Recursion is somewhat dangerous. So, this was a function that we wrote. If I write it in some kind of algorithm type of statements, and I say that you know, function recursive and int of n, this was a function of this kind. If n equal to some 1, then do something, else we said return 1, let us say, return n, else we said, else it was like recursive is equal to n plus recursive of n minus 1. It is something like this. If I was going to write it in pseudocode, the program would have looked like this. So, this was a harmless statement, and then you found that the time complexity was order n. Now, suppose I replace this n here and make this recursive of n minus 1. What will happen to this program? Okay, let us see what will happen. The best way to analyze this is to draw what is called a recursion tree. So, I started off with the topmost recursive of n, and what do? I divide it into, so it is going to call recursive of n minus 1 and recursive of n minus 1, and this one in turn is going to call what? Recursive of n minus 2, recursive of n minus 2, and this recursive is also going to call recursive of n minus 2 and recursive of n minus 2. Okay. Now, what is the issue with, and then n minus 2 will call n minus 3 and so on. Let us start with recursive of n is 8, then this is going to call 7 and 7, or maybe instead of 8 let me start with 4, it is easier. 4 calls 3 and 3, 3 calls 2 and 2, 2 calls 1 1, and that is when it will terminate. Calls 2 2, 1 1, and it finally terminates. So, now if you look at this computation, which was order n originally, now if you look at the, what is n now? N is 4. So, now if you look at the number of computations, 1 2 3 4 5 6 7. Okay. So, basically 7 times the recursive call is being made, and therefore, this one's time complexity in terms of 7 is of the order of 2 to the power n, and this is something you must be very careful when you write recursive programs, okay, because this is all constant time over here. So, it becomes order of the exponential in terms of 2 to the power of n. So, imagine if it was 8 here, then what would have 8 given? It becomes 7, 6, 6, 5. So, there are 4 5s here, okay, 5 5 5 5 and so on, and you notice that the tree literally starts growing very very large. Okay. So, you have to, but the best way to in my opinion to analyze recursive programs is to simply draw this recursion tree and count the number of nodes that are there in the recursion tree, and that will give you exactly the amount of time the program is going to take to execute, like we saw in this case big O of 2 to the power of n. Okay. So, on the other hand, I can also have here recursive is, let us say, recursive of n by 2 plus recursive of n by 2. You guessed it, right. So, what is happening now? 4 is getting divided, becomes 2 2, 2 becomes 1 1, and we are done. Okay. So, how many times it is? Basically this one 1 2 3 and into 2 perhaps. So, it is only order n the time complexity of this algorithm. So, these are things that you must keep in mind when you analyze the time complexity of recursive functions. So, we will stop here and then we will take two algorithms for sorting and searching, and we will analyze the complexity in little bit of detail.